All right, so let's continue. We're going to continue with chapter 12, section 2. To recap, we define one-to-one functions and onto functions. And a function that is both one-to-one and onto, we call that a bijective function or bijection. Okay, so we're going to continue talking about how to prove that a function is onto. Okay, so look at the definition of it. It's onto if every element of B gets used as a second coordinate. So for every element of B, every little element B, there's a little a such that f of a equals b. So if I claim that a function, I want to prove that a function is onto, I'm going to take an element, a little element of set B, and I've got to produce this a. I got to show that there is an a where such that f of a equals b. Okay, so that's how you show that a function is onto. All right. So let's over here is. All right. So proving a function is onto. So you think of it as if I claim that f from a function a from a to b is onto, I'm claiming that every b shows up, every little b in this set shows up as a second coordinate. Okay. All right. So the template goes like this: you let little b be an arbitrary element of the set B. Okay. Then somehow I've got to show that there's a little a that gets sent to this B. Okay. So I need to somehow explain how to find or construct an element A in set A such that f of A equals B. Okay, and you can conclude that f is onto. Okay, so that's the template for proving a function is onto. Take an arbitrary element of B, and then you got to find that little a that gets sent to that element B.
So basically, a situation where if they gave us an ordered pair, then you would just show that.
Well, here's sometimes you're given the equation of the function, and you can just use the equation of the function to like given any function, any element of B, then you could actually use the equation of the function to find. I want to show you an example of that. Figure out what a you would need to plug in to equal this for f a to equal b.
So we get number 5 in the homework again.
Mm-hmm.
This gives you an ordered pair.
Okay.
So would it be like an existence proof in a way?
Yes. You're showing that something exists. Yeah. So you take an arbitrary element b, and you got to figure out what would you have to plug in that function to make it equal b, make the function value equal b. So I'll show you in a second. All right. Prove that the function f from the rationals to the rationals defined by f of x equals 3x plus 4 is onto. Well, think about what that says. If I claim this function is onto, that means you pick any rational number, and I can find an x to plug in so that 3x plus 4 equals your rational number that you chose. Okay. So we're going to pick any. We're going to let pick any arbitrary rational number, and then we're going to figure out what you have to plug in for x so that this equals your arbitrary rational number. All right. Here's the proof. Let little b be a rational number. Well, what we need to do, we need to find a rational number A such that f of A equals B. That's what our job is here. If we can do that, then I'll be satisfied that f is on 2. So oftentimes you need to do some scratch work here. So I'm going to kind of take a break here. I mean, you do this on a separate sheet of paper, but I don't happen to have a spare chalkboard at the moment. So let's find. So here, let me do my scratch work here. Okay, again, this is kind of like behind the scenes of mathematician's job. You do some scratch work on the other side, and then you just happen to shout out, oh, your next line, well, let's let A be B minus 4 all over 3. I mean, so that's kind of stuff you don't show people how you came up with that. But here's the scratch work. So we want f of A to equal B, right? We want f of A to equal B. But f of A would be 3A plus 4, right? Just using the equation of the function. F of A, if I just plug in A for x, 3A plus 4. So I want 3A plus 4 to equal B. So you just solve this equation for A, and that'll tell you what you should be plugging in. Okay, so solve this for A. So 3A equals B minus 4, and then divide both sides by 3. So looks like A should equal B minus 4 over 3. Okay, so that's, again, the scratch work. You don't write that in your proofs. Okay? All right. So we need to find an A so that when I plug it in the function, f of A equals B. Okay. So you get your scratch work here. You do that on another sheet of paper. Okay. So the next line you would just say, all right, well, obviously let A equal B minus 4 all over 3. Okay. Remember, all I've written is choose an arbitrary rational number B. Now I'm going to choose A to be this number, B minus 4 over 3. Is this still a rational number? Yeah. Because a rational number minus 4 is still rational. A rational number divided by an integer is still rational. So this is still a rational number. And A is a rational number. But moreover, what do you get when you plug in A into this function? F of A is the same as f of B minus 4 over 3. Okay, that's what A equals. Okay, now let's plug it in. So I'll get 3 times this input, 3 times B minus 4 all over 3, plus 4. And when I cancel the 3's, you get B minus 4 plus 4, which, lo and behold, equals B. Okay? So if you give me any rational number, I can find an input, A, so that f of A equals your rational number. Okay. Give me any rational number, B, and if I'll choose B minus 4, all divided by 3. And that's what's going to work. Okay, so I might say something like n f of A equals B, and f is on 2. Okay. Any questions? So I constructed, I showed that there exists an A such that f of this number equals B. So that's one. Any questions? Chose any arbitrary element of the real rational, and I constructed an A that gets sent to that. All right. How about how could a function not be onto?
There's a B that doesn't have an A.
Yeah, if there's an element of this codomain that doesn't get mapped to, or doesn't get an A sent to it. There's an element of the codomain that isn't used as a second coordinate. Okay, so let's show that let's prove that a function is not onto. Prove that f from the integers to the integers defined by f of x equals 4n is not on. Could you tell from looking at the equation that it's not going to be onto? So you're plugging in integers only. So I'll put x here. Sorry, f of n equals 4n. I use n because the inputs are all integers. Like I could use x's on that. But f of n equals 4n. So all the numbers you're plugging in are integers, but look at all the numbers you're getting out. Are you getting every possible integer? No, you're only going to get multiples of 4. So this can't be onto, because the only outputs are multiples of 4. So here's how a proof would go. You have to show that there's some integer that isn't used as a output. Just use anything that's not a multiple of 4. Like how about consider 1, which is an integer. Then f of n equals 4n will never does not equal 1 for all integers n. There's no way you can plug in an integer n to make 4n equal to 1. There's no way 1 could be an output for some input n. So f is not onto. I mean, it's one way to say it. You could even, in this case, you could even just say stuff like the outputs are all multiples of 4. So any integer that's not a multiple of 4 won't be in the range of this function. Okay. The range of this function is only multiple of 4. Okay. All right. Any questions? Yeah.
Can we look at number 4 on page 202?
The number 4 page 202? That's why I didn't assign?
Yeah. I mixed it up. I thought it was number 5 initially.
But I did get insight on how to do number 5. Yeah. So the number 4 page 205. I didn't really talk about functions like this, but this one you wanted to go over before?
Yeah.
This is a function from z to z cross z. So I didn't go over these. I kind of skipped them on purpose because this is the outputs. So you take an integer, and the output is an element of z cross z. What do elements of z cross z look like? They're ordered pairs. So you take a single element, and the output is ordered pair. So technically, elements of this function would look like n, comma, m, but this looks confusing, so oftentimes you just drop these extra parentheses and just, it's kind of like that. But so another way of saying it is that instead of saying f of n, well, f of n equals an ordered pair. Let's just say m and p. Okay. And so these functions. That's why I kind of skip these because they're more difficult. You plug in one integer and you get out an ordered pair. but these are also integers. M and P are integers. Okay. So I personally didn't assign that or do it, but does that help with the notation though?
Yeah, like
this one is
function.
it's f of n. They define their function as f of n equals 2n comma n plus 3. So it's like so what is f of 1, for example? F of 1 would be 2 comma 4. So you get, for plugging in one integer, you get out an ordered pair. So yeah, I mean you can still do the same type of thing. Like they ask you to do show it's 1 to 1.
So for that case, you would just do it like 1 to 1 for the first term, and then 1 to 1 for the second term.
Well, if it was 1 to 1, I would still start out with assume f of x equals f of y. And you still start with that. It's just that f of x would be 2x comma x plus 3, and then f of y would be 2y comma y plus 3. And then you got to show the x equals y.
Basically, like double the amount of work.
Yeah, it's right, because you'd have to show each coordinate. This would have to be a 1-to-1 function. This would have to be a 1-to-1 function. All right, so any other questions from 12.2? Okay. 12.3 is kind of a neat theorem. I'm skipping it. It's called the pigeonhole principle. You ever heard that before? You probably use this concept in real life without even really thinking about it. Like if say we've got 5. How many days are left in class? 5, including today. Say I have 6 sections left to cover, but we only have 5 classes. Can I teach 1 section a day? No. So that's what the pigeonhole principle says. Then there has to be at least 1 lecture where I do 2 sections. I mean, so that's an example of the pigeonhole principle. So you guys understood it without even. So here, why is it called the pigeonhole principle? Because you have all these holes for pigeons. You know, you have, say there's 3 holes and you have 4 pigeons. Can you put 1 pigeon per hole? No, you're gonna have to have double up and put 2 pigeons in 1 pigeonhole. So that's kind of the concept. That's where the name comes from. But you can reinterpret that any way you want, like I just did with sections of a class or. Okay, so that's kind of. It's kind of a neat theorem. You might see that in another class, but I'm going to scroll it now. The next thing I want to do is 12.4 on composition. And I guess since we're starting a new section, it might be a good time to take a little minute break or so. Take a minute break, and then we'll start section 12.4 on composition of functions. Remember that stuff from calculus, pre-calculus, like F composed of G, and G of F, or F of Hogging off, yeah. Question? Well, if you take the function and compose it with its inverse, you should get X. Yeah, we'll talk about that too.
I got tried to, as I finished you do it earlier, there's NaCl over Na or OH.
Over what?
NaOH. That basis under a salt.
The basis under salt. Yeah. 2 peanuts, so walking down a dark alleyway. One was assaulted.
Oh.
So, wait a second. So, what was it? NaCl over NaOH. So that equals chlorine over hydride, or what is it called? What's OH? It's, yeah,
I don't. I haven't done chemistry in a very long time.
You say oxygen hydrate.
It's like dihydrogen oxide. You've heard of that? It's a compound that's found in almost every chemical in a home, and yet people, it's unregulated. I mean, people have dihydrogen oxide.
Come on, Hannah. The other one's still inside.
Still inside?
Well, because we looked on the internet and it only one girl can. It says that the other one is still left and she's never gonna drop it. But the last time the mother said she couldn't feel it, so she thinks he just. I know. Yeah, something extremely hard.
Okay. Let's talk about composition of functions. Okay, so you probably have some notion of composition of functions. You've taken calculus, you've seen composition of functions are very, very important concepts when you're taking derivatives or you need to decompose the function as inside and outside parts and things like that. So let's talk about, we'll define composition. So here are three sets, A, B, and C. F is a function from A to B, right? There's exactly one arrow from every input of A to at least to one, exactly one element of B. So F is a function, right? F is a function from A to B.
Neither one-to-one nor opposite.
Yes, neither one-to-one nor opposite. But G is also a function. It's a function from B to C, right? There's exactly one arrow pointing from every element of B. Okay, so G is a function from B to C. Okay. Now the composition of these two functions, I'm going to start with an element here in A, and then go to the intermediate codomain here B, and then send it to element C. So G, the way I'm going to write this is G composed with F. G composed with F. Now, it's kind of, when we read things, we always read from left to right in English. But when you're doing this operation, you actually, it goes from inside out. So F is like the first function that's being evaluated, and then you take the function F and you're plugging it into G, as we'll see. So this function is actually a function from A to C. So F goes from A to B, and then G goes from B to C. And then G composed with F goes from A all the way to C. Okay. So here let's write out the elements of F. F has elements 1, comma P, 2, comma Q, 3, comma R, 4 T, and 5 T. Okay? has elements px, qx, rz, sy, and tw. Okay, so the first element of the set. All right. So when we look at G composed with F, you start with an element of A and follow the arrows. So what happens? So since it's a function on A, it's got to have exactly 5 points, right? The first coordinates are 1, 2, 3, 4, and 5. Right? If it's a function from A to P, each one of these elements of A is going to have exactly 1 point, one order pair. So here's how we do it. So 1 gets sent to P, and then P gets sent to X. So G composed with F is the point 1 has the point 1x in it. 2 gets sent to Q, and Q gets sent to X. So 2x is also in G composed with F. 3 what? 3z. 3 goes to R, then R gets sent to Z. So 3z. 4 goes to T, T goes to W. And then 5 goes to T, and then T gets sent to W. So 5W as well. Okay. Any questions about that? Well, that's how you, in a set like this is how you do composition. So you take an element A, then like 1 is here. F of 1 is P. F of 1 is P. Then you take F of 1 and you plug it into the G function, and G sends F of 1 to X. So G of F of 1 is X. Sometimes you read it, and I said the composition of G and F, or G composed with F, but often it's read G of F. So G of F of 1 equals X. So it's a little about prepositions. Any questions about this example? So I've shown you an example of a composition. I haven't really defined composition. Okay, so let's define composition. You're taking an output of one function and plugging it into another function, and that's how you get composition. Okay. Definition. Suppose F is a function from A to B, and G is a function from B to C. The composition of G and F denoted by G with a little circle and then an F. The composition of G and F, denoted G with F, is the function defined phi okay. So G of F of X, the definition is you take F of X and you plug it in the G function. So that's why the composition of G and F is often called G of F of X. A lot of times I'll just say, when I'm reading this notation, I'll even just say G of F of X. It's a little easier than saying the composition of G and F. Okay? So think about the last example. We took an element of A, we plugged it into F, and you get out F of X. So or we plug in an X, and you get F of X out. you take that output f of x and you plug it into the g function, and you get the output g of f of x. Okay. Note, g is a function from g composed of f is a function from a to c. You're plugging in elements of A, and the outputs are now elements of C. And you got to go through the B, the intermediate code of A. Okay. Any questions, Bob? Okay, so let's hopefully match it up with your knowledge of composition from calculus, pre-calculus. Here's another example here. Let f and g functions. F from the reals to the reals, a function from the reals to the reals, and let g be a function from the reals to the reals. We define by f of x equals x squared, and g of x equals x plus 5. And let's do the composition of g with f. Okay, so this function is also defined on the reals. The inputs are the reals, and the outputs are in the reals as well. So the composition of g with f is g of f of x. So by definition, you take the function g, and you're plugging in the equation for f. Okay. So the equation for f, so f of x equals x squared. So if I take x squared and I plug it in this function, you get g of x squared. So if you plug in x squared, wherever you see an x, you replace it with x squared, you get the equation x squared plus 5. So that's the formula for g composed with f. Okay. Start off with a real number, plug it into f, you get x squared out. You take x squared, you plug it into the g function, you end up with x squared plus 5. Any questions about that? Now you can reverse the order, and so it's important that even though we read left or right, when you're evaluating these compositions, you think of f as the inside function. You actually work from inside out. So f composed with g is also a function. We can also define it because the if I go from reals to reals, then I can take that real number and plug it back into f and get another real number out. So then f composed with g is also a function from the reals to the reals. It's defined by f composed with g of x. Now, you take the function f as the outside, and g is going to act as the inside function. Okay, you take an x, plug it into g, you take g of x, and then plug that into the f function. Well, g of x was defined as x plus 5. So this is f of x plus 5. The definition of f says whatever you plug in, you square it. So if I plug in x plus 5, I should get x plus 5, the quantity squared. Okay, so that's the equation for f of g of x, or the composition of f and g. Okay, any questions? All right. What about f composed with f? What's the equation for f composed with f? F of x. So what do you get at the end of the line here?
X squared squared.
X squared squared. Yeah, so it'd be f of x. So f of x squared. But x squared, if you plug in x squared into this function, whatever you plug in, you square it. So it is x squared squared.
X to the 2 times 2 power.
Yeah, you could simplify it as x to the fourth. But for emphasis, you might do it like this, just to emphasize the fact that you plug in x squared into the x squared function. But it simplifies to x to the fourth. Questions about compositions? I got a few theorems about compositions. I'm going to wait. I'm going to hold off probably till Monday, so that way you can do some homework with compositions. And then there's a few theorems I want to present. So I'm going to come back to section 12.4. But for now, let's talk about inverse functions, which is in 12.5. We're getting close to being done with functions. I want to do some stuff in 12.5 today, and then we'll come back to 12.4 on Monday. And I'll basically wrap up this book, and then I want to spend a little bit of time on graph theory. All right, 12.5 inverse functions. So if you recall from calculus, pre-calculus, inverse functions are very useful. They're kind of all over the place. In you see these like arctangent, and even we'll look at exponentials and logarithms or inverse functions, and they're all over calculus and analysis. So inverse functions are important. Yeah. So we have this kind of bad notation for inverse functions. You have a function, and then its inverse is has a -1. There's another inverse. Where does that come from? I mean, because so if you have like a real number 2, the multiplicative inverse for 2 of 2 is 1/2. Right? So 2 and 1/2 are we call them multiplicative inverses because 2 times 1/2 is 1. But you can write 1/2 as 2 to the power -1. So that's where this notation comes for inverse functions, which I don't like. Because you have things like, the inverse tangent. Well, does that mean 1 over the tangent, or does that mean the inverse tangent function? This means inverse tangent, obviously. It doesn't mean 1 over tangent. But if you did like x to the -1, that's not the inverse of x, that's 1 over x. So I don't like that notation. Usually from the connotation, it should be clear what we mean. But
What would they decide to put like a capital I as the power for inverse?
yeah. All right. So given a relation. Let's talk about the inverse relation. So given a relation R from A to B, okay, if R is a relation from A to B, what does that mean? What does R look like? A relation from A to B. It's a subset of A cross B. Okay? So a relation from A to B is just a bunch of ordered pairs. First coordinates are in A, the second coordinates in B. Okay? All right, so imagine taking every ordered pair that's in this relation and just changing the first and second coordinates. Interchange the first and second coordinates. So if xy was in your set, you just flip them, and you now get a point yx. Okay. So if you do that for every single point in the relation, you get a new relation. It's the inverse. It's called the inverse relation. It'll be a relation from B to A.
So B cross A.
Yeah, it'll be a relation from B cross. It'll be a subset of B cross A. So that's called the inverse relation. Okay. So given a relation R from A to B, the inverse relation of R, denoted by R to the minus 1, to look like an exponent, minus 1. Okay. Is a relation from B to A defined by if the set of all yx such that xy is in R. So you take all the order pairs in R and you interchange the coordinates and make that a new set. That's called the inverse relation. Okay. Quick example. This is a relation at 3 points, 1, 2, 3, 4, 5, 6, and the inverse relation would contain the points 2, 1, 4, 3, 6, 5. Okay. Just switch all the coordinates.
So
I didn't define what A and B are, but I'm just giving the general. If this was a relation from A to B, then the inverse relation would be this. Okay. Let's look at another example. Function F. Okay. So look at the relation F. Right? The relation F contains order pairs 1A, 2C, and 3B. Okay. So as I wrote it using F, but just consider it as a relation. It looks like this. So is this a function from A to B? Yes. There's exactly 1 point for every little a, every little element of every element of capital set A. There's exactly 1 order pair for the first coordinate. Okay, there's actually one order pair with 1 order pair with 2, and 1 order pair with 3 as first coordinates. So this is a function. Okay. Let's look over here. G. So this is the function G here. So what order pairs are in G? 1A, 2A, and 3C. Okay, is G a function from A to B? Yes. G is a function from A to B. It's not onto, yeah. It's not onto because B isn't used as a second coordinate. It's not one-to-one because two inputs are getting sent to A, right? So f of 1 equals f of 2, but 1 doesn't equal 2. So it's not one-to-one. Yeah. All right, so let's look at the inverses. F inverse is A1, C2, B3. Okay. My question to you is this a function from B to A? Is this a function from B to A? So a function from B to A would have exactly one, for every element of B, there's exactly one ordered pair with that first coordinate. There's one point with A, there's one point with B, and there's one point with C. Exactly one. So the F inverse is a function. Okay. What is the set G inverse? It's A1, A2, C3. Yeah. All right. So, is this a function from B to A?
No.
No. Why not? Yeah. So for the input A, there's two different outputs for the input A, and another reason why is B is not used as an input. Okay. All right. So you got to figure this out, right? What's special about F that G doesn't have? What characteristics does F have that G does not have? F is 1-to-1. There no two input, there's no two arrows pointing at the same element of B. So F is 1-to-1. Oh, I heard that. Somebody said it's bijective. So it's 1-to-1 and it's onto.
So the function is bijective and it has an inverse.
Well, in this case, I've only shown you one example, but maybe that's the theorem coming out. Yeah, so your insight serves you well. So a function. If a function is bijective, it's 1-to-1 and onto. Forget the fact that I said that last class, but so if a function is bijective, then its inverse is a function. Okay, F is 1-to-1 and onto, and so its inverse is a function. Okay, G is not 1-to-1, nor onto. And if you're missing either one of those characteristics, its inverse is not going to be a function.
Makes sense. Linear algebra for a matrix to be invariable to the rules that the matrix equation AX equals B has to be 1-to-1 and onto.
They use the same, criteria. Yeah. So if a function is bijective, then its inverse relation is also a function. Okay. If F from A to B is bijective, then F inverse from B to A is a function. Okay. It is a true statement. And you see why that has to be. It has to be onto because when you reverse it, every one of these has to show up, right, as exactly once. So if it never uses a second coordinate, when you reverse them, they wouldn't show up as the first coordinate, right? Like B didn't get used as a second coordinate, so when you flip the coordinates, B doesn't get used as the first coordinate. Okay. Now here, if two elements are getting sent to A, so when you reverse the coordinates, that also violates it. You have A is not used exactly once; A is used more than once. Okay. So that's really how the proof goes. If for a function to have an inverse that's a function as well, F has to be 1-to-1 onto, or a bijection. That is the theorem. And then we'll use some time. We'll compute some inverses of functions. whoever's watching this video will pause. Hey, Mark. All right. So, okay, back to this board. Oh, theorem. Function f from a to b is bijective if and only if its inverse, that inverse from b to a is a function. So it's actually an if and only a statement. So a function is bijective, then its inverse is a function. If the function's inverse is a function, then that function must have been bijective. Okay? And you can kind of see why, from this example, why it has to be true. And if you use for this to be a function, every element of b has to show up exactly once. Well, that means that it has to show up at least once. I mean that must have been onto, but it has to show up exactly once. You couldn't have more than one, so it had to have been 1 to 1 as well. That had to be 1 to 1. So, all right. Let's see. How about how do you compute an inverse? Do you remember doing this like in a college algebra or a pre-calculus or calculus class? So if you start with an equation y equals f of x. Okay, start with y equals f of x. So if you have just a set of points or ordered pairs, I mean, you could just, if it's finite, you could just sit there and just switch all the x and y coordinates. But when you have a function with an infinite number of ordered pairs, all you have is an equation, usually. Like f of x equals x squared, or that's not bijective, but f of x equals x. You have an equation, so in your equation, you switch the x and y coordinates. So you interchange the x and y coordinates.
So y inverse equals f of x.
So I'm going to interchange the variables. So you'll get x equals f of y. So you'll have this new equation where you switch the coordinates x and y, switch the variables x and y, and then you got to solve for y again. If you can solve for y, then you solve for the formula for the inverse. Okay? So solve for y to get, if you can solve for y, you'll get the formula for the inverse function. I'm going to show you, some examples. Okay. So you exchange the x and y coordinates, you get a new equation, you solve that new equation for y, and then you have your formula for the inverse function. So, here, let's use this here. Okay. F from the reals to the reals, defined by f of x equals x cubed plus 1. You know what the graph of this function looks like?
What do you do? What does that do?
Something like that. Okay. So f of x equals x cubed, the cubic function would pass through the origin, but you shift it up 1 unit, it would look like that. Okay? So graphically, do you remember how to tell if a function is 1 to 1 and onto? Yeah, so 1 to 1 means it passes the horizontal line test. You can't find 2 points with the same y coordinate, second coordinate, right? So this function does pass the horizontal line test. It's onto because this arrow keeps going down forever, and this one keeps going up forever. So every height is hit somewhere along this curve. So every real number is going to show up as a second coordinate. So this function is one-to-one and onto. It is bijective. Okay, so we can guarantee now that this does have an inverse. All right. So these
Start off with this equation, y equals x cubed plus 1. Okay, y equals x cubed plus 1. And here's this equation you start with, then you interchange the x and y's. Okay, so x equals y cubed plus 1.
So if a point satisfies this equation, then any point on the inverse function will satisfy this equation. You just interchange x and y. But now let's solve for y. So I get x minus 1 equals y cubed. To get to y, I'm going to take cube roots of both sides. So y will equal the cube root of x minus 1. Okay. So you're not always, for any odd power, this will work. You can take like the 5th root or the 7th root, and you will still end up with a function. But you can't take square roots and 4th roots. Those are not bijections. Like f of x equals x squared. It's not one-to-one. It's not onto either. So this is the formula for the inverse function. So the inverse function would be f inverse of x equals cube root of x minus 1. Okay. So this function, f of x equals x cubed plus 1, and f inverse of x equals cube root of x minus 1. And have you seen this trick? If you think of this as the set of points, right? A set of points. If you exchange every x and y coordinate, well, what you'll get is a reflection across the line y equals x. So if you did this like one point at a time, like this point would be 0, 1, well then the point 1, 0 would be on the graph. This is the point like negative 1, 1. Negative 1, 0, I mean. Negative 1, 0 will go to 0, negative 1. So you end up with a graph that looks like this. You take this graph and you reflect it across that line, you'll get this graph. And it looks, so this is the graph of the inverse function, cube root of x minus 1. The cube root function looks like that. And it's actually, the basic cube root function shifted to the right one unit. Okay. So here's f of x. And here's the graph of inverse x. Okay, any questions about that? So that's how you actually compute an if you have the equation of a bijective function, you replace f of x with y, and then you interchange x and y and solve for y. Give you the formula for the inverse function. Something else that's interesting to check, you could. If you take, let's think about compositions. What if you take f of f inverse of x? Well, let's see what we get. So here's f. The cube, you cube something in the input, and then you add 1. If I plug in f inverse of x, I'll get the cube root of x minus 1. Okay, if I cube the cube root function, I'll just get this stuff on here, and then x minus 1 plus 1 is x. If you take f of f inverse of x, you get x. Similarly, if you plug in x cubed plus 1 into this function, x cubed plus 1, if you plug it in for x, the plus 1 and minus 1 will cancel, you have the cube root of x cubed, which would equal x. So it is a fact that if you take a function and you you compose it with its inverse, you get x. But also, if you take f inverse and you compose it with f of x, you also get x. They're inverses. One undoes the other one. Like if I plug x into here, I cube it and then add 1. If I take that output and plug it in here, I would subtract 1 and then take the cube root, and so I'd be right back at where I started, the x. That's one way you can check to see if your formula works, or your inverse works. For an example of my bijective function inverse, how about f, a function from the real numbers to the positive real numbers, defined by f of x equals e to the x. This is bijective. So it's not bijective onto all real numbers, but it is bijective onto positive real numbers. Okay? Remember what the graph looks like? E to the x. Like that. So here's a question for you. Are there more real numbers or more positive real numbers? There's the same amount. So, isn't that weird? Because here's a bijection, right? I mean, if you give me any real number, I'll tell you which positive real number to match it up with. I'll match it up with e to the x. If you give me a real number x, I'll match it up with e to the x. So since they're in one-to-one correspondence here by this function, there has to be the same amount of them. Isn't that weird? So there's the same amount of real numbers as positive real numbers. All right. So let's find f inverse. Okay. Actually, so this function f inverse is defined from the positive real numbers to real. All right. So we start with the equation y equals e to the x. You interchange the x and y, so x equals e to the y. And then what? Yeah, so this is why logarithms are logarithms are invented. You can't solve for an exponent using a basic operation like addition, subtraction, multiplication, division. You have to have a new operation. And so we define an exponent like this and by using logarithms. So if x equals e to the y, then y would equal the log base e of x. But the logarithm base e is by the most commonly used logarithm. It has its own notation. So write that ln of x, or natural log of x. So this is our inverse function is the natural log function. This will work for any exponential. If you use like 2 to the x, or 10 to the x, the inverse would be the log base 10 of x. Here's the line y equals x. Okay, so here's f of x. If I reflect this across the line y equals x, I'll get this function. Looks like this, and that is your natural log function. So very, very, very important, functions in mathematics, naturals and logarithms. Okay. Any questions about this example? inverse of e dx is the natural log. The inverse of the natural log is e dx. What's the opposite of a natural log? Duraflame? There's artificial logs.